Good morning, everybody. My name is David Bonifacic, and I am the CEO and a founder of WB Engineering. WB Engineering is now in our 25th year, and we started WB during the dot-com era of the 1990s. And here we are presenting on a new emerging technology called quantum computing. And digital computers have really been making it easier for us to process information for decades. Quantum computers, on the other hand, are a completely new approach to computing. They have the potential to solve very complex problems that are way beyond the limits of today's computers. It is definitely one of the next big trends in tech. And now, right now, all we hear about is AI, but quantum computing is an up-and-coming game changer behind AI. Quantum computing as a market could be as much as 1.3 trillion in value by the year 2035, which is not that far. And this is according to McKinsey Company. And that's why we're here today, because this is a growing industry and there are some important things to keep in mind about the design of the facilities to accommodate quantum computers. And that's where we've gotten the experience to talk about this subject. So I'd like to introduce our speakers. Ray Doyle. Ray Doyle is managing director of our science and technology practice. Ray came to WB and he said he wanted to work on science and technology projects and has built a successful national practice for us over the past 15 years. Ray is based out of our Raleigh office. Bart Stewart. Bart is a managing director of our Washington, D.C. office. Bart just celebrated his 15th year with WB. And the unique thing about Bart is he spent most of his career engineering data centers. So this subject is close to his heart. And Scott, are you back, Scott? Thumbs up?
I am, yep.
All right, good. Scott Kantner. Scott is our team leader in our Denver office. In the addition to the work that he manages for our team in projects in critical facilities and science and technology, he has managed projects in 19 countries through his work with the U.S. Army Corps of Engineers, and he's currently on base in Missouri, and I thank you for your service, Scott. So with that, I'll lead it to, let me just, before we go to the, I forgot one thing, logistics. Please, we encourage questions. This is a tech-heavy subject, so anything that, sometimes there's some questions, please don't hesitate to put it in the chat. I will monitor the chat and try and interject questions as we go along. But towards the end, we'll unmute everybody and we'll just have an open discussion. And this will give you the opportunity to talk and ask questions directly to Ray, Bart, or Scott. So with that, I'll hand it off to you, Bart. Thanks.
Thank you, Dave. All right, so to start off, we want to address the big question. What is quantum computing? So simply put, quantum computer is a computer that uses quantum mechanical principles for operation. So where a standard computer relies on a continuous flow of electricity, a quantum computer relies on manipulating single subatomic particles to do its operations. So I'm going to spend a very small amount of time giving you a little overview on the two main quantum mechanical principles that really drive all of this stuff. It's not critical that we all know the ins and outs of this, but when you're talking to people, it's good to know some of the language that they're using. So first off, we have Heisenberg's uncertainty principle. The first thing about it is the idea that measuring a subatomic particle will change it. That's not that crazy of an idea. Just think about anytime you use a tape measure and you put that metal flap on something, a very, very small amount, immeasurable amount of particles are going to get rubbed off, and it will, in theory, actually change that measurement. But on a macro scale, it's inconsequential. It's not within the accuracy of that tape measure. Same thing happens when you're looking at subatomic particles, where looking at it does change it. The difference is at that subatomic scale, it changes it completely. You can change the direction something spins, you can change how fast it's moving, you can change where it physically is, all by measuring it. Moving on to where it gets a little weirder. When a particle is created by a source, for a light source creates a photon, that photon does not have a position, spin, or velocity. It lives in a wave of probability. So we talk about waves in quantum mechanics. It's a wave of probability, and it's not a matter of whether or not we can measure it. It actually physically does not have a position. And then similarly, this idea of, if you have ever heard the term superposition, because it related to not having a position, it is also in multiple places at one time. And then lastly, we got quantum entanglement. So when that light source creates two matching photons, they are going to be entangled to each other. So they can be light years apart from each other, and measuring one and changing that one will actually change the other one instantaneously. So that's a form of faster than light information transfer, which we still don't as a species fundamentally understand. And just to put it in perspective, this stuff is all very counterintuitive. When these theories and the math were developed in the 30s, Einstein said it was crazy and he wouldn't get behind it. And it wasn't until the 70s and 80s where we actually had the technology to prove it that everyone really kind of got on board with these really out there ideas. So I'm going to move on to Scott, who's going to talk a little bit about how we actually harness those and turn it into computing power.
Thanks, Bart. Einstein is wrong. That's what I heard out of that. That's fantastic. All right. So to understand, Bart mentioned we are harnessing quantum particles to essentially do some computing. We're harnessing some of those quantum mechanics, and it's down to the single quantum particle level. So let's understand how that relates to computing. In a standard computer, we're looking at bits. Bits are electrical signals. It's either, it's an on or off. As we code inside of a computer, we call them bits, and we represent them as a 1 or a 0. We use transistors as logic gates to read, to create, to process that data. As we then get into quantum computing, our base unit is not a bit, it is a qubit, a quantum bit. Qubits have a little bit more than just a 1 or a 0. They're more than just a on or off state. So the state of quantum particle, as Bart mentioned, isn't known until it is measured. So it could be anything. It is essentially nothing until we actually measure it. The state now is reliant on two quantum variables. So I like to think of it as a smart light bulb. We went from having your light bulb is either on or off to now a smart light bulb. You can program a range of different colors and a range of different brightnesses. So two variables. And depending on what you plug into your smartphone to tell your whatever brand smart light bulb to be, you won't really know what it's going to look like until it lights up in that room. You might think you're getting a beautiful shade of fuchsia, and it's going to look beautiful in the room, program it in, and it shines on the room and you hate the result. So you don't know what you get out. The bottom line is because there are two variables that go in and they are all indeterminate, there is a infinite range of potential solutions that could come out of that qubit once we manage to harness control over it and measure the result that comes out on the other end. That creates an indeterminate potential outcome. All right, so that's our base unit for these two, right? Now let's go in backing up just a little bit, the evolution of computers. Computers, 1930s, the Turing machines, we're looking at large pieces of virtually viable because not all of us have space for this massive room size computer, and because they are not easy to operate. 40 years later, we finally get the MOSFET, what we know now as a microprocessor. It's all of those transistors on a die, a very small little black chip on site on a circuit board that does the processing for us. We are shrunk down to a much smaller scale than that original Turing machine, and everything along the way. So long transition period. Now they are commercially viable. Now they can be fit into our hands, fit onto our desktop, so on and so forth. 2020s electronic computers are even smaller. We're looking at components sized down to where they fit in our hands. So we've come a long way. Backing up a bit, during the development of computers in a simulated environment, Richard Feynman was the first person to posit the notion of a quantum computer. The notion being that if our computers are trying to be used to simulate, quantum research, he said, well, what if we use quantum physics to create a computer? Wouldn't that then be able to better simulate the quantum environment, allowing us to better understand those environments and continue our research just into quantum mechanics and quantum physics? So that kind of kicked off the notion of a quantum computer. Over the 4 decades that have gone since, there has been gains made, but a lot of those gains have been in the last 20 years. The reason being that computers themselves were advancing so quickly, quantum computers weren't necessary. Here we are in the 2020s, and quantum computers have become far more relevant recently due to where we are with electronic computers and the fact that those are finally starting to slow down in their development. That being said, quantum computers at this stage are very much in that early research stage as electronic computers were back in the 1930s. So you can take the 2020s and kind of likened it to the 1930s. The Turing machine took up rooms to operate. It took massive amounts of power. It was not functional. I could not take a Turing machine, put it on my desk, and use it for something. It required researchers, it required lab facilities. And that's where we are in the 2020s still for quantum computers. Quantum computers, we don't have a single technology that we could say is the lead in quantum computing. We have multiple different quantum particles and multiple different lab-based technologies that can manipulate those particles to create a quantum computer. So we're looking at a couple pictures on the slide here. These are 3 leading lab-based technologies that allow us to create quantum computers. Now, they are not the only things out there. There are other technologies out there. They don't get smaller at this time, at least. And it hasn't gotten to the point where any one of these have won the race to be the lead quantum computer that might someday size down to be commercially viable. But we're looking at nuclear magnetic resonance that's using powerful electromagnetic fields to stabilize and control quantum particles. That is very heavy, literally. It is very power intensive, and it requires isolation from outside EM interference in order to operate correctly. We're looking at cryogenics in the middle photo there. That is a dilution refrigerator. Doesn't look like any refrigerator any of us are used to seeing. But that's cooling. Cryogenics in this case is cooling down to near 0 Kelvin in order to slow down those quantum particles and again, stabilize and control them so that they can be measured and they can give us results as a computer. So that's a dilution refrigerator. Again, it's requiring a lot of power to support chillers, potentially liquid nitrogen systems for the cryogenics. A lot of power, very heavy, and they often require some increased deck heights in our buildings because they have frames to support them, and those can be very, very large. And then our bottom photo is just a close-up of a photonics optics table. And in this case, we're using lasers to manipulate photons, which are a subatomic particle, to use them as our qubits or our base unit for our quantum computing. Optics tables are used because in this case, we are very sensitive to vibration. We have to be in a very stable environment. Often clean rooms are necessary. And the room, we did a project out here in Denver not too long ago with a photonics-based quantum computing lab. And they not only required a lot of power, but they required a lot of clean power. So we had to use filters on the power, and we had to use a UPS to ensure that they had consistent clean power to power their lasers that they're using on their photonics lab for their quantum computer. In this case, in all 3 of these cases, we're looking at fairly large rooms, large labs. The photonics labs, they had multiples of them, one for each computer basically, but they were 500 square foot clean room environments. Not something you're going to find in your everyday commercial space, as we're not at that stage yet. I want to emphasize, very much still in the R&D stage. So that's how right now we create a quantum computer. We expect in the near future, 2030 and on, they're going to get smaller, but that's where we are now. As far as what they are then good for, why the increased emphasis on quantum computing now? Want to look at a couple key applications: cryptography, artificial intelligence, and simulation. So these are all applications where you require a very large amount of processing power in order to get to an answer on the far end. Processing power that is beyond what our standard, computer processing units, central processing units, are capable of with a digital computer, but at which quantum computers, with their indeterminate capability, are much better at. In the case of cryptography, our one of our first, not necessarily commercially viable yet, but one of our biggest quantum computers that's out there, and actually just got superseded a month ago by the same company, was at 500 qubits. So 500 qubits, relatively small overall quantity, but that's the biggest they had. As of a month ago, 1,000 qubits beat that out by the same company. And that quantum computer is a dilution refrigerator, cryogenic-based quantum computer. Cryptography, that computer was able to beat, on a brute force attack, AES 128-bit encryption in a matter of minutes. Now that's critical because that same type of encryption is considered unbreakable by an electronic computer. It takes billions of years for an electronic computer to brute force break AES 128 encryption. And one of our very early R&D quantum computers at 500 qubits was able to break that in a matter of minutes.
And
Huge
Scott,
capability.
so people understand, that level of password protection, for lack of a better word, is banking, it's military, it's how far up the food chain is that?
Yep, that's everything. So AES 128-bit was developed in the early 2000s. Well, AES was developed in the early 2000s, and it applies to just about everything we have out there. Your Wi-Fi is encrypted with it. Your internet communications for your bank, your whatever, are encrypted with it. Your VPN's encrypted with it. AES 256 is a standard for military encryption, DoD and federal encryption. And with that, AES 256 still hasn't been broken even by quantum computers, but the speed at which that quantum computer can break 128 indicates that as those computers grow, they very likely will be able to break AES 256 in the near future.
Thanks,
And
Scott.
that brings the next side of this equation, which is not just quantum decryption or breaking code with quantum computers, but creating the next level of encryption using quantum computers. And I think, Bart, you have an example of why that's extremely pertinent.
Yeah, so we talked about the decryption. We're using a quantum computer to decrypt what the encryption that a digital computer made. So if we have quantum computing create the encryption, circling back to the idea of measuring a particle changes the particle. If you're using quantum encryption, if somebody tries to eavesdrop on your data, it changes it on the other end. So when that data comes in, it has changed, and I therefore know that somebody has been trying to eavesdrop on my data. So that's a pretty game-changing thing. It doesn't necessarily lock it, but knowing that somebody is trying to read it, they've got a tap on your wire, is a really big step in preventing data stealing.
Yep. So fantastic capability, basically a changing checksum that allows you to verify that your data is still secure. But also, just with quantum encryption, the increased power of those computers, we should, and there are multiple in development, better encryption technologies to beat out AES 256 for the day that is finally broken. Now, that I'm not going to directly go into artificial intelligence and how that improves those worlds as well. The bottom line in both of those is they are environments that require a massive amount of computing, and quantum computers give them that, the large amount of processing power. Just as Richard Feynman suggested that quantum computers might be able to better simulate the quantum environment, it is proving true that because they are capable of simulating such a large environment, they can simulate down to the subatomic level, which has massive capabilities when it comes to material science, pharmaceutical, simulating how a theorized material will actually operate in the real environment before you try to build that material. Simulate how a drug will interact with a human body before it ever goes to clinical trial is huge, to the speed at which these researches are able to be developed.
Yeah, and
All right.
just the computing power aside, digital computers are really not good at random things. You guys ever had one of those early MP3 players and it had a random feature and you noticed that it actually played the same songs in the same order? That was a digital computer trying to be random. And that's the same way it is now. Even in a better computer, a random algorithm, it's still an algorithm. It is still trying to simulate randomness with a digital machine. Whereas there's so much randomness inherent in quantum mechanics that a quantum computer is always going to be better at simulating randomized things than a digital computer will. All right, so Ray, why don't you talk about our actual buildings and tenants a little bit?
So the interesting thing Scott and Bart shared was that I find the whole thing a little scary, but also extremely exciting for society. But back to the root of what we do, we help people with real estate and buildings and building systems. And so, how does this all come back to what's important to the buildings and the tenants themselves? And we're going to start at the just kind of regional considerations is this idea that this new technology and new science is taking place where the talent exists. And it's happening all over the country. But as you can imagine, it's happening in a lot of the regions where there's already a lot of science and tech work happening. Places like Boston, places like Silicon Valley, places like Denver, the growth areas in Austin and Raleigh and just DC. And then the military centers, as Scott pointed out, are definitely where a lot of the talent takes place as well with defense contractors. So that's where a lot of this is going to start. It's going to grow from there. What's also important is the fact that we have a lot of expensive buildings and a lot of expensive systems and pieces of equipment. When we get into this R&D world, we end up talking about things that aren't mainstream. They're not everyday use. So it's going to take a lot of money. There's a fair amount of government money that's going to fund this through grants. There's going to be venture capital that's going to want to try and be out there in front of it. So there's going to be a strong need for a large amount of funding. And then the last thing is this idea of clustering of companies. And, that again, we talk about talent, but we also talk about where the companies are and how some of these IT and technology companies are going to grow together. Much like the biotech sectors and clusters grow around the country, we're going to see a lot of these same companies end up in similar areas, and they'll tend to steal employees from each other and technologies from each other, and we'll see what happens in that front. But one of the interesting and fascinating parts about the Denver area, which Scott mentioned a little while ago, is the U.S. Economic Development Administration had dubbed the Denver area as a regional technology and innovation hub for quantum innovation. And there's over 70 small companies in the Denver Boulder area that are, kind of spearheading this technology. So it's exciting to see it in a local area where we're located, but also to see the growth of quantum computing happening today.
So moving from the region inward, talking a little bit about site considerations. So the first thing that we always think about when placing these buildings is ground vibration. As Scott alluded to earlier, vibration is key for a lot of these different technologies, and making sure that you are not near train tracks, near a planned construction. We had a project a couple of years ago. It was a quantum computing lab where they had the physical site, they had bought the building and were getting ready for construction when somebody learned that a metro line was going to be built a couple hundred yards from the building. So not only were they going to have to live through years of construction vibration, then deal with trains coming by continuously after that. At that point, they already owned the building. So at that point, we were looking at, all right, what mitigation strategies can we put in so that those vibrations outside don't get translated into the building and into the lab and into that optics table.
And in addition to the ground vibration, one of the labs we built here for quantum computing in Colorado, one of their major concerns was EM spectrum interference. Now, there's a lot of things that were involved in the actual construction of the lab regarding that, but one of the key considerations for siting would have been ensuring that we weren't near any potential outside interference. So that would mean power lines, or some kind of satellite field, something that is emanating electromagnetic radiation that is potentially going to interfere with the equipment inside of the lab.
So we talked about the region, the site. Let's talk about the actual building itself. So thinking about the core of the building, the low vibration. We need low vibration. That's going to be a requirement for pretty much any quantum computing tenant. So to accomplish that, we need a stiff structure. Stiff structure means more steel, more concrete. Going through a recent study that we did, to stiffen the building as was recommended to meet the vibration criteria that we were targeting, was $500,000 of additional steel in the building. So not a project killing dollar amount, but definitely something that needed to be budgeted for. And the last part in that kind of core and shell design is this idea of modular MEP strategies. Scott talked about high power loads, high power needs. That lends itself very well to a modular construction, where you put in risers day one, but you don't need to put in all of the equipment day one. And you can hold off on that capital investment until the tenants are lined up and ready to move in, and you add additional capacity as that happens, rather than having to put all of it in day one. So moving a little farther in, we got the tenant spaces. The interesting thing here is we've seen a fairly wide swing of lab space percentage. So we've seen it as low as 20% quantum lab, 80% office, as high as 80% lab, 20% office in an incubator scenario. So most people are going to be somewhere in between, but it is a wide variety. And outside the lab, a tenant space that is fairly standard tenant space. Yeah, you want to talk a little bit about the actual equipment that we're going to see in the physical lab itself?
Yep, and I did want to add one thing to the two items you just mentioned, which is that part of the reason, none of the items Bart mentioned are items that you would normally see in a bio lab or a chemistry lab. So part of the differential here is these labs are different from what we're used to seeing in our R&D space. That goes along with the equipment that we're going to be seeing in there as well. If we're talking about the science and tech industries in Colorado, this is an important one, or anywhere in the country, this is an important one, but it looks a lot different from the ones that we're used to seeing. So some of the equipment, and I alluded to some of these earlier when I was discussing these types of sciences, they do vary greatly depending on the type of quantum computer being built. In the case of our photonics labs, obviously we'll have optics labs and high power lasers. One of our examples for that, one of our labs required a high power laser that could only be served off of 480 volts. So not something that you'd usually see in a piece of equipment plugged into that is sitting on a table in the middle of a 500 square foot lab. Optics kit tables are being used because we need that, besides the stiffness of the building, despite this fact that the site might be very low vibration, those optics are very sensitive to any ground movement. So isolating them with optics tables, often active optics tables that are going to require compressed air in order to fill up their airbags and provide that additional isolation. We've also got in our cryo labs, we're looking at cryostats, dilution refrigerators, chillers, and other equipment that is necessary to reach the target temperature inside of those. What you're seeing kind of behind that that word there is a dilution refrigerator. Again, doesn't look like in a refrigerator you've seen. It is being suspended by a frame specifically built for that dilution refrigerator. You can see it is quite tall in the lab that it's in. And you can also see that it's fed by piping. That is most likely from a nearby chiller. So not only is the size of the frame, the dilution refrigerator, going to take up quite a bit of space in the lab, but there are chillers nearby that can often take up a lab support room in order to keep everything at the temperature it's supposed to be at. In the case of some of these, with the photonics labs, with some of the other labs, we're also going to be looking at clean rooms. The photonics, in addition to being very sensitive to vibration, EM interference, are also sensitive just to particles in the room, because that can interfere with your optics. It can interfere with your lasers. So in the case of one of the projects we did in Colorado required a ISO 7 clean room. Another one required an ISO 5 clean room. So it just depends on the project, if clean rooms are going to be required at all, and to what level they're going to be required. That brings obviously a lot of HVAC into it. It doesn't bring outside air in like we'd expect with some other types of labs, but there is going to be a lot of HVAC in that ceiling for the HEPA filtration of our airflows in those labs. And then finally, this is a less common one, but it is still worth mentioning. Some of these technologies, a very small subset, can run on basic circuit boards, and you may see some basic circuit board development in a lab. And that brings with it all of the chemical requirements, the fume hood requirements of circuit board manufacturer. Now, that is a very small subset. That is a very rare one. But like I said at the beginning, the technologies vary greatly. So while a lot of these are power dependent and stability dependent, we do still have some that will require some of the chemistry and hazardous materials we expect in other types of labs. Moving on from the actual equipment then into the labs, and some of this is a little bit redundant, but just kind of going through them again. External isolation, I did talk about EM interference. I did talk about isolation tables. Those are pertinent to a lot of these. We're also even just looking to the level of external isolation, meaning we probably don't want exterior windows in some of these photonic labs. Well, we definitely don't want them in the photonic labs, because exterior windows means we have exterior conditions, sunlight coming in, affecting the temperature in the lab, adding EM interference into the lab, adding just UV rays coming into the lab that could potentially affect some of our science. I mentioned power density a number of times. Important to this is not only just the day one density, the amount of power available, but the clean power being available, both to NMR and to photonics. I know Bart's had projects where the power coming from the utility was not clean enough for NMR. And so they had to install power filters and a UPS system to ensure they got clean enough power to the systems. Now, that means that not only is your NMR heavy and requires a lot of space in the lab, but you've also got a room next door now with battery banks, UPS, power filters, large amounts of heavy equipment that needs to go find some floor space and take up additional room in your lab. And that leads into my final item on the list here for micro areas, which is high structural loads. Whether we're talking about sorry, bouncing around a little bit. Whether we're talking about the UPSs, the NMR, the vibration tables, any of those, we are expecting relatively high structural loads for most, if not all, of these technologies. So something that is beyond what your standard office building can provide, certainly, and beyond what a lot of labs, more starter labs are capable of.
Scott, and everybody, we have a question. Can you expand on what clean power entails?
Yeah, so the clean power has to do with how smooth the sine wave is. So we have alternating current. So we have a sine wave that's our alternating current to create the power. So there's two different parts of it. One, there's the smoothness of the sine wave. So a dirty power, it can be a choppy sine wave. It can have pieces missing. The peak isn't where it's supposed to be. So you get inconsistent results on the outside. And the other side of it is just the voltage fluctuation. So you always want to have a consistent voltage through your system. When you hear about harmonics, that's related. Anytime you have harmonics going through a system, what that's doing is it's taking your sine wave and it's making it messy. So what these things really want is that nice, clean, arcing sine wave. And if you give it a dirty sine wave, it's not going to work properly.
So what is the component that fixes that?
So you have a power conditioner. So it's usually two pieces of it. So you have a power conditioner first, and that's the first thing that's going to really smooth out that sine wave. They're normally it's a collection of specialized transformers in one combined box. You look at the thing, it doesn't look like anything special. It's a box with wires coming in one side and wires coming out the other side. But inside, you're going to see large windings of big specialty transformers. And then from there, you're going to go to a UPS because the power conditioner cannot boost the voltage necessarily to what you need it to be. So once you've cleaned the power, then you've got your UPS that's going to protect you from any blips or brownouts or sags in your voltage by supplementing it with its stored battery power. So your UPS is going to take that sine wave, it's going to rectify it, it's going to reinvert it, and give you a nice clean thing that's exactly what you want.
And you don't mention generators. Is this the type of lab that if you lose power, you lose a lot of research?
So in the case of our quantum labs that we put in Denver, they did want generator backup because they would lose research. If they had any kind of blip, they would potentially lose days, weeks worth of research, and they needed to keep power up to keep their computers up at all times.
Okay.
Yeah, our projects in Maryland was the same requirement. We had generator backup for the UPS, all of the mechanical systems in the labs themselves.
Gotcha. Thanks.
All right. So then the last thing, Scott touched on it briefly, with the clean rooms come high velocity air. With high velocity air comes a source of vibration. So designing those clean rooms in such a way that you get that volume of air that you need and you get that cleanliness that you need from the filtration without creating vibration on your table is a whole little specialty.
So key takeaways. There's a bunch of key takeaways, and I'll just give you guys a second to kind of understand how complex this system is and how the spaces are very detailed to the science that we use. So these takeaways are going to be things that you want to look at from a high level down to a detailed level. So we start with the big picture site issues, vibration. We've talked about it a bunch. We've talked about structure. We've talked about why it's important. But the takeaway that I'd like to leave you guys with is this requirement that before you site a building or you pick a location for your quantum computing, you go and you get the state, city, and county maps that will define future development for mass transit, busways, high voltage power lines, even just highways in general. Any of those developments could impact your building and your ability to do the science once you're in that building. So it's important to know before you site your location to understand what's around you. And then inside the building, we talk about building equipment. And this isn't just the equipment that's inside the lab that Scott went through in detail that some of the technologies are used. It's really about the vibration that is created by the HVAC equipment or power equipment that's going to support that lab. Most people don't understand that, you hear a transformer hum, there's vibration generated by that transformer as it transforms the power. We want to make sure those are in a location that's not going to disrupt the science inside the space. Things like that want to be on grade. Things like chillers, cooling towers, pumps, any of those things that you can isolate on grade, either in an isolated slab or even on grade outside, detached from the building, can greatly impact or greatly improve, I should say, your ability to do better science in the lab.
You know, on the airflow side, we actually were brought in to solve an existing problem where there was high sensitivity optics, and there was a single diffuser that was blowing right down because it had to have that HEPA filtered air, and it hit the top of that equipment, and with the distances, it made you couldn't see it. You look at the thing, everything looks perfect. You touch it, you don't feel anything. But when you're looking at these, you know, this millionth of an inch or even smaller, you know, looking at the nano scale, things move at the nanoscale, and it was throwing off their ability to measure properly. So I had never seen that before. That was new to me on that project, and that was a fun problem to solve. And then talking about local sources, they're going to need stuff. So, you know, Scott mentioned compressed air. I think every single one we've done had a compressor. They want it close to the lab because that's where they're using it. Compressors vibrate, they're loud, they shake. So you got to move. So in, you know, our particular case, they were adamant they needed compressed air near the lab before we identified how stringent the vibration criteria were. We ended up having to change the design and move the compressor basically to its own little building outside the building, and put it in a little shed, feed compressed air in there so that we didn't create new problems with it.
Great. And to everybody, the mic is open, so if anybody wants to ask a question, please feel free.
So, and I'm going to touch on this one briefly. Scott mentioned it earlier that we have a higher ed client in the DC region who had actually installed their NMR without doing any sort of power studies, and it didn't work. And now they're scrambling to spend huge amounts of money on a power conditioner and UPS for something that they already want to be using. So not only did it cost a lot of money they didn't plan to spend, but now it pushed them back 6 months before they were actually able to use their $1 million NMR machine.
So the one thing I was just going to add on that high density power, and we talk about clean power, but the high density power is also very important. A typical R&D lab building would have somewhere between 8 and 12 watts a square foot of power available to the tenant in the lab. And when we get into things like quantum computing, you're looking at anywhere from 30 to 50 watts a square foot inside the lab. So the amount of power needed to do this science is much higher than a typical R&D building. And we need to make sure that when you're looking at siting a building or looking at siting a space inside a building, you're taking that into account. So a key takeaway is make sure that you have looked into that and verified it. And Bart mentioned power conditioning. I always say you should test that power before you look at the site. There is dirty power out there on the grid. And in some cases, you're going to have to pay a lot to condition it. To Bart's story at the university we were dealing with, better to know in front of it than react to it later and have to use all your contingency money on something you weren't planning on spending it on. And then we talk about high power needs. High power needs turn into high sensible heat loads, which is just the need to reject the heat that's generated inside of the lab. And when that happens, you end up with a large heat rejection system. And that can be chilled water, it could be refrigerant, it could be air. Any of those heat rejection systems generate vibration in the space and then also create problems for you to mitigate later. So understanding that those high sensible heat gains are going to be something you need to deal with, you can plan ahead for where those things will be located to mitigate that vibration. The one thing on the sensible heat gains I'll add to that, in some of these spaces, Scott talked about photonics and optics. There is a key point here when we talk about calibration, and calibration based on airflow and calibration changed on temperatures and humidities. If you have a rate of change of temperature or humidity that happens too quickly, that can disrupt the calibration of the optics and the equipment inside the space, and then you have to restart your whole experiment. So stable control of HVAC to meet the needs of this high sensible load is equally important.
Thank you, Rich.
And then when we try and use as many of these simple analogies for the people that have been following the biochem and biotech world lately, there's little in common in a lot of ways. to a quantum computing building and a quantum computing lab, I'd probably say there's a better parallel between a quantum computing lab and a data center than there is what most people think of as an R&D building, which would be biotech or chem labs. And the biggest difference is the fact that in a biochem and biotech lab, you need large quantities of outside air to exhaust the fume hoods and containment devices. And you also have to deal with a higher percentage of hazardous material spaces. When you do quantum computing, you're going to find that you just need more power and less outside air. So the analogy in the project we studied was you needed, to increase the power transformers and switchgear to do quantum computing. And they said, well, what if we'd made it a biolab? And I said, well, then you need more outside air. And in that particular analogy, that particular project study, we were able to verify that about $100,000 worth of money was needed to increase the outside air. And if they reduced the outside air, they could use that same $100,000 worth of budget to increase the power. So there's a competing factor there, and you just need to balance those two when you're looking at these buildings and understand where you're going and make sure that you've studied those two concepts. And here's one of my favorite slides because it's about as simple as it gets. So I'll take us back to like third grade, maybe fifth grade, I don't know. Times tables. Some problems are really simple, and you can kind of know and you can memorize what happens on the left side. And then there's some problems that are much more complicated, but you don't think about it being that hard until you were asked that question. And that's where they think quantum computers are taking us, to solve these really complex problems that have multiple iterations. You can add decimal points after the 2 and the 3 and see how complicated that question can be, and start to understand that there's a big difference between the two. I like to say that we need engineers to solve the problems in between the two, and that's what we're here to help you guys with. So if there's any questions we can answer, I'd love to stick around a little longer and go through those.
I just have a general question, Ray. Cost. What do these labs cost? They sound expensive.
They are expensive, and we talk about labs, and I'll get the analogy between biotech and quantum computing. It's a great question because at the baseline, they're about the same cost. So if you're somewhere between $600 and $1,000 a square foot for a fit out, a complete fit up, kind of built to suit biotech lab, you're going to be in close to the same dollar value to be able to do a quantum computing lab of the same size. It's just pick 50 to 100,000 square foot building to answer your question, Dave. The challenge that we find with some of our clients is that they want to be able to do both. They want to have this high power density, but they also want the ability to do the outside air. Now that building, we always say when you add flexibility, you add cost. That building, to be able to do both, now exceeds that $1,000 square foot. You could be into $1,200, $1,400 square foot, because now you're trying to achieve both goals to be flexible for both tenant types. And that's where it gets a little tricky, and you got to study your options.
Right. Great. If we could, everybody on the call, there's a little QR code. If we could kindly take a picture and fill out the survey, that'd be greatly appreciated before I forget, because I always forget to say that. So thanks for everybody. And in terms of how do they make money? Is anyone commercially viable? Or this is based on grants, research dollars, etc.?
So most of them are still operating on some amount of venture capital money. Was our client here. They're a spinoff at a university in Maryland. Did go public last year.
They did.
Yeah, so they are getting funding from a much wider pool. They did have customers. They did have, were customers of theirs that did pay, but it was largely paying to get an opportunity to figure out how they would use a quantum computer. So rather than them developing their own, they're saying, all right, we want to develop software that would harness a quantum computer. We want to rent your space. We want to rent space on your quantum computer so that we can work on developing our software for when this stuff does become commercialized.
So they're way ahead of the curve.
Yeah.
Dave, companies like IBM and maybe less public, some of the bigger tech companies, and you could imagine who they are, the Googles, the Facebooks, the Apples of the world are probably, without public display, doing research in these same topics.
Understood. Great. So doesn't sound like we have any more questions, guys. Here's a question.
We had the discussion.
Yeah, I do have one question. Typically for, when you're fitting out a building, you can do all kinds of surveys, the mechanical systems, the electrical systems, and so forth. Since these are so specialized, is there any testing agencies or groups that can come in and do vibration analysis or a seismic analysis of the building shell itself at the beginning of a project?
There's a lot of companies that do that kind of testing, third-party independent companies that specialize in vibration, and they will come in and do a baseline for you, and they can do it based on the site. They can do it based on the accelerometers they can bring in and measure the vibration in the slab, whether it's on grade slab or elevated slab, and let you know where you are. And what that helps you do is define what you need to do in your project. That could be stiffening the slab, that could be moving something that's already there that's vibrating to grade. It could be just putting in passive or active vibration tables to mitigate that vibration. So those baseline tests, no different than getting a baseline power conditioning test. It's an important way to kind of head off a potential change order or costly exercise to impact something you didn't know about.
And you're going to do that test before and after construction also, because you're going to have very specific criteria for that construction, and you're going to have specific performance criteria that your general contractor is going to be held to, and so you want to be doing those vibration tests as soon as the work is done, before there's actually people trying to use the lab.
Good questions.
Dave, I have a question. For these groups that are kind of at the cutting edge of developing new technologies, you don't have equipment cut sheets to look at often. How well are these clients able to define their own performance requirements?
So that's a great question, and it can be a really fun part of the project for us, because to your point, they really don't know, and it ends up being a very interactive process to work through with them and figure out what that design criteria is. I know that, IonQ in particular were very much in their infancy. They knew they needed low vibration, but they didn't have a number that they could put to it. So that was a challenge that we had to work through. So we ended up with a vibration specialist who, has his typical, I don't know if they have charts or I'm not a vibration specialist myself. And he was able to guide them through that process. And similarly on, the cooling power side, we went and, they took measurements of some of their existing equipment and then had to make estimates about what that would grow to in the future. So it was, they did not have a lot of that coming into the project.
And similarly,
now I'll add on there. So one of the advantages, kind of surprising, but Ray mentioned the Quantum Consortium approved by the Economic Development Association for Colorado. That's 70 different companies. So those are 70 different companies that are essentially working together under that consortium. And so some of the companies actually made the equipment that goes into the lab. So it was a case where they actually knew their equipment very well, or at least what today's version of those equipments were very well. In the case of their dilution refrigerators, their lasers, etc. What they didn't know is exactly what they wanted in the lab. They knew that, for their future requirements, hey, we have these dilution refrigerators, these cryostats, these lasers, these optics tables, etc., because somebody in that consortium built every single one of those components. But how many do we need for, what are we going to be able to do 5 years from now? They were very much just kind of predicting where their science was going to go. So their day one, we knew exactly what it would look like. Their day two, is a much harder equation to solve for.
Michael, I was just going to add to the comment on what does the equipment really need and what does the science need. I mentioned the rate of change of temperature and humidity being the concern. The original criteria from one of the clients was, plus or minus a half a degree and, 2 or 3% RH. And Bart and I looked at each other and said, that's going to be really, really, really expensive to build an HVAC system for that level of controllability. And then we started asking why. We tried to ask the basic question, why do you think you need that? And he would pull out cut sheets on some tiny little sensor that is part of his rig. And then we realized that sensor was all about calibration. And then when we realized we could help him by saving money, by pushing him towards this idea, it's rate of change, not the fact that it changes by a couple degrees or a couple 5 or 10% in RH. It's the fact that it happens slowly. So as Bart said, that is the fun part for us, digging into the complex side of the science that they're dealing with, but it's not the manipulation of photons or particles. That's not what we do, but understanding how the equipment needs to work in the environment it needs to be in is definitely the exciting part.
Good question, Mike. Anything more with that?
I do have one additional question. I remember reading a fascinating article years ago about a Japanese company that was a leader in high precision measurements, like for machining complex parts. And they had actually built a subterranean, kind of like a vault, to do their really critical measurements. And I wonder if you've heard any discussions at all that might lead you to think that in the future, once they prove or flesh out the concept a little more, that an optimal solution may be to go subterranean instead of above surface buildings.
So that's
I'll
fascinating question.
grab that one.
Okay.
The structural isolation we're seeing these days can range. So it can be, if we're looking at slab on grade, one of our projects, they wanted us to create an isolation slab. So we cut out underneath each lab where their photonics or their optics tables were going to go, so that they could repour that and repour it so it's structurally isolated from the building and has better structural isolation. In an ideal world, we want this technology to get less touchy. We want it to, go from very complex lab to very uncomplex lab to commercial office space to being, on somebody's desk at home someday in the future. So we would hope that it doesn't go the subterranean route. That is a means of, creating that extremely high level of isolation. But we're not seeing that in the current science, that level of isolation being necessary in the current science. And I'd like to believe it's going to go less isolated as we move into the future and not more.
I actually think for IonQ, between when we started the project and when we finished the project, they'd actually already made steps in making it less sensitive.
Yeah, in the case of the one of the firms that we worked with here in Denver, their initial computer was highly sensitive to temperature variations, required that highly isolated slab, required all of the EM considerations. It almost looked like a Faraday cage around that room because they were so concerned with EM. Their next stage of their computer was a lot easier. It still required a clean room, but it didn't have the temperature concerns, it didn't have the RH concerns. They were able to do it on standard optics tables. They didn't need an isolated slab. So kind of the same experience there. They went from highly sensitive technology to a little bit more still sensitive, but getting closer to the mainstream.
Terrific, guys. We're approaching our time. We're past, and just want to, unless there's any more questions, just would like to thank everyone for joining us, and I hope this was informative. And guys, great job. I learned a lot. So thank you very much, and hope to see everybody in the next one.
Thanks, Dave.
Thank you.
Thanks, everybody.